Renyue telling us about the global preventive external negative feedback on galaxy formation due to giant radio lobes. Welcome.
Does it work? I lost my voice. Can you hear? Okay, good. I thank Joe and Avishai for the invitation, and trying to reduce the title, but that's the best I came up with. Too long, but the talk may sound a bit non-conventional. That's because it is. Before my talk, I'll say a word about a conference I'm organizing in Hangzhou. So Hangzhou is one of the biggest cities you never heard of, because there are bigger ones like Beijing and Shanghai. But next to Shanghai, it's on the coast, like the Bay Area, and the date is middle of November, October, and that's the best time to come, if you like. Okay, so we got 3 UNESCO sites, so you won't get bored, even if you don't attend the conference. Okay, so the main question is, in galaxy formation, in one word, is that why 8%? And it's known since the early 90s that if you don't have feedback, including the gravitational feedback already, but without additional feedback, about 1/3 of the baryons will form into stars. So clearly you want to suppress that. And if you look at how gas has gone slow over the history, about half of the mass will be in halos when the first generation of halos form. That's about redshift 20 to 30. And each halo now has doubled their mass about 20 times or more. And each baryons, if follow dark matter, 40, then will have lived in 10 different halos. So it means that in each halo, in each node on this tree, that you only have less than 1% of star formation efficiency. It's very, very inefficient. And if you look at the suppression required, the apparent suppression effect goes increased towards both high mass end and the low mass end. And apparently you need at least 2 different kinds to accommodate this non-monotonic effect. And there's a maximum star formation efficiency or minimum suppression around halo mass about 10 to 12 to 12.5 solar masses. So the 2 most important energy players which can affect the star formation on the galactic scale are the supernovae and the supermassive black hole feedback. And without doubt that if you have energy and momentum coming out from these sources, you're going to affect star formation, okay? Locally, sometimes you compress the gas, is a positive feedback. Sometimes you heat up the gas or drive the gas away, it's a negative feedback. But it's still unclear, at least to me, that each of these 2 players can do their assigned job. And this one is somewhat of a logical point. So if you look at the specific star formation rate, it's a strong increasing function with increasing redshift, meaning that the star formation is much more vigorous at a high redshift than at a lower redshift. But if you look at the galaxy luminosity function, it's actually steeper, meaning that the smaller halos or smaller galaxies are not being affected much when the star formation is the strongest and the supposed supernova feedback is the strongest. Whereas if you go to lower redshift, below redshift 2 or so, and there's a dramatic, pretty sudden transition, the LF slope goes to -1 from -2. And that is when the feedback is supposed to be the weakest from the Madar plot. So in the sense that the supernovae, the far too blown away blue wings and drive the gas away, and that's obviously could happen, and we see happen in galaxies, and it makes total physical sense. But we are still not seeing it, at least collectively for dwarf galaxies as a population, or in differential across the dwarf halo mass. But how about the internal aging feedback? By internal, I mean is the conventional way you have the gas landed in your galaxy, drive away. Okay, you have a ballooning machine treating aging. But let's put our personal views aside, look at some of the evidence that we see observationally. And here, what's plotted here is in these little dots, different colors, is the population without aging at the center. And the crosses are the 6 PG quasar. And here the focus in central kiloparsec, so the star formation surface density. As you can see, that the ones with quasars in the middle tend to lie above the trend, as indicated by the inclined, the shaded region in each panel. So if there's anything, it's a positive aging feedback, or maybe more likely that a gas flow coming in that's both triggering the aging activity and the enhanced star formation. So that now becomes a supply question, not demand and driving gas away that the galaxy don't like. If you look at the amount of molecular gas in galaxy with quasars, but across the spectrum of luminosity, you can see the legend is probably a little bit wrong. So look, the square is their work. So you can see that across 4 decks of L barometric, and if you look at the upper panels, the trend is essentially flat. So there is no indication then when the luminosity of the AJ increases, the gas, the cold molecular gas decreases and seems independent. What's happening and what's happening on the galactic scale in the center seems to be not affecting each other. And you might say, okay, then the radio jets might also help, in addition to the wings that people normally invoke. Here is an excess of star formation rate in radio loud quasars minus radio quiet quasars. So as you can see, the excess is a positive number, meaning that if the radio jet is doing anything, it's enhancing the star formation. Okay? And again, more likely it's the gas driving the triggering of the jets, also making more star formation. Again, that's the gas supply. And when you look at the ISM dynamics, so what's plotted here is X is the weight, and the vertical axis is the ISM pressure. And the top left panel is the ones without quasar, and the other 3 have a quasar in the center. And if you look at general trend, there's no indication that the quasar is somehow disrupting the ISM dynamics, making it different. And more quantitatively, the amount of kinetic energy that couples to the surrounding baryons over the barometric appears to be less than about %. And the current implementation in most of simulations is a few % or so. So it's not clear that some of the implementation is well supported by observational evidence. Still, it must be due to stellar evolution and the supernova feedback, because there are no other significant players can reduce the star formation rate. The question is, how does it operate? So I like to advocate it is not inside-out driving, but rather the outside-in prevention that could make the difference. Okay? So one player that we know and we observe and we know it's very energetic is the radio jets. It comes in two forms. FR1s, which are more suppressed, you see them in intracrustal medium and more sort of suffocated by overhead material. But the FR2s, they can propagate much further, like a laser gun, get out, eventually got slowed down by the accumulation of the resistance over the longer distance, eventually going to stop and expand. It's overpressurized. And if you look at energy comparison, so here's a very simple calculation. So that for the supernovae, 100 solar masses give you about one supernovae, give you about 0.3 BeV energy. And now radio jet has 100 times the Magollin ratio, 0.2%, times 1% of radio FR2 fraction of all galaxies at a high redshift, times 0.05 jet making efficiency, to get to about 0.2 BeV. And the conventional AGN wings, again, 100 times 0.2% times 0.1 is radio efficiency, times 0.01 as the number I put in the previous slide from observation more optimistically. So all these three numbers are comparable. So you have a three-horse racing, so which one is winning? Now, what would nature do? So if you have a baryon already landed in your galaxy, you want to push it out. The amount of energy required is the baryon mass times the dispersion squared of your system. Okay? But if you heat up the gas at in remote distance where the density is low and you raise the entropy, and you raise entropy such that the gas won't be able to come into your galaxy because no matter how you squeeze it, without cooling, the entropy is conserved, and you couldn't create high entropy gas than your systems. Oh, okay. All right. Okay, so we have done some simulations. So we have individually evolve a FR2 bubble in separate simulation, and then we put into cosmological simulation. So these are MHD simulations. And so this is our simplest first try. So at redshift 2.5, we put in these little bubbles, and then we evolve. So we run simulation redshift 100 to 2, stop, put it in, run again. Okay? Then we compare the ones without these jets and with jet, and see what's the difference. And here is a comparison of a couple of halos, just one halo in this case. This is a variant of a figure in the paper, but the paper is embargoed, so I cannot show you paper. And you can see that due to the injection magnetic field and your shock structure will be different, the accretion will be different. So here you compare the upper panels to the lower panel density and on the left, and temperature on the right, and the things affected. And on the bigger panel on the left, the contours indicate magnetic field. So here is magnetic field. Here's along the line side. You can see the change of direction from red to blue. And they switch on the order of a couple megapascal scale. So they're coherent on the megapascal scale, then they become incoherent. Now, physically, what's happening here is comparable to the thermal suppression due to temperature. Basically, when the Alfvén velocity of VA is greater than the dispersion of your system, of your halo. Equivalently, that when the plasma beta is less than 1, then the gas will not be able to accrete, okay, onto the halo. At least will be hindered significantly. Here is a plot. X is the ratio of Alfvén velocity over the velocity dispersion of the system. And the y-axis is the amount of mass ratio in the simulation with bubbles and to the one without bubbles, without radio bubbles, radio jets. And as you can see, just as expected, that when this x reaches about 1, meaning that the Alfvén velocity is equal to the dispersion of your system, you can see that the mass accumulated in the halo is being suppressed. Okay? An important point is that the suppression is inhomogeneous across space because some galaxies live next to a jet, some don't. So galaxies in the voids, for example, will not be affected at all. Okay? They will still happily forming stars even today. The galaxy in the voids will be relatively blue. But in more overdense regions will be more suppressed. Okay? And this also may explain the one I mentioned about the evolution of the slope of the galaxy luminosity function, and because this radio jets formation peak just around the Madar peak, and they're cumulative and they don't dissipate. The reconnection time of the magnetic field is much longer than the Hubble time, and they accumulate, and so most of the effect will occur at the redshift below 2. And that is where you see the transition or the flattening of your luminosity function. And there are some other puzzles why that magnetic field, outside groups, and the clusters where the wind up by differential rotation doesn't occur, have a field on the strings of microgauss or more. And our simulation seems to be able to account that. And I don't have time to show all these consequences. And another possible effect we found here is that the baryon would be suppressed and on a scale of a few megapascal. And that is exactly where the weak lensing signal is strongest. And you see a so-called S8 effect. And here I show the yellow, the brown curve is the ratio of the power spectrum in the simulation with jets over the ones without. As you can see, there's a suppression order about 17% or so. And dark matter also feel that effect, but not as much. But overall, the middle curve show you that there's order of a couple percent suppression in the power spectrum that could help. But I know in our simulation, we only inject magnetic energy, which only makes about 3% of the total energy. Most energy is in the thermal and the kinetic of these bubbles. Okay, but this 3% already making a difference. So I think if we put in the remaining 97% of energy, and this will be a much larger effect. So I put up my takeaways here. So thank you.
Thank you. We have time for 2 quick questions while the next speaker is set up.
Thank you. So I agree with a lot of the arguments about the easiness of preventive feedback. The thing that I'm worried about, that I'm sure you've thought of, is we know that in clusters, things like rotation measures and other things tell us that it's like beta of 100 or something like that beta is much larger than 1. So does that get preserved if you have such strong fields preventing accretion, or is it because you're preventing it at early times and the thermal gas is not nearly so hot, so it works then?
So here the one feature I didn't emphasize is that the suppression is again differential. It's like you heat up temperature to 10 to 7 Kelvin, then the cluster can still accrete, but your small galaxy cannot. So it's similar effect here.
So the
In other words, the rich cluster will not much affected at all. It's a small groups and
so is the
smaller
argument that in the
galaxies.
CGM of those groups you'd see beta less than 1?
That's right.
Okay.
David.
I was going to ask about the magnetic field, and it seems to be an important part of your picture. I was wondering how those magnetic fields behave in the filaments that are actually out in the cosmic web rather than clusters, which I can understand that you can model. Do they affect, are filaments important in the grand scheme of?
Yeah,
Okay.
so this might look like a filaments here, across this way, okay? And there's a big variation. So as you can see by the outermost white contours, the field there is, I forgot the number, but something like minus 7.5. So, and then going in, get to a microgauss. And there's big variation, but in many cases, it could reach 0.1 microgauss. Yeah, yeah. But the general IgM still a nanogauss. It's not much affected.
Okay, let's thank, we need to move on. Let's thank Renyue again for the talk. And next we have Shyam Menon telling us about star formation and feedback interplay in compact starbursts in the early universe. And this is the last talk about poster session. So it'd be great if online attenders can tell us if sound is okay.
Hello, can you hear me?
Okay, cool.
All right, can everyone hear me? Awesome. Good morning, everyone. My name is Shyam. I'm a postdoc at Rutgers and the CCA, the Flatiron Institute. And today I'm going to be sharing some insights on the feedback star formation interplay